Can you see my screen, guys?
Yes.
Yes.
Okay. 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 Hello, everyone. First of all, thank you for attending this workshop. I hope it would be full of knowledge and fun and entertaining, and to add much more value to your process of thinking and your way of thinking. The problem is people still keep coming. Okay. So I'm gonna be starting right now. So for the people that they don't know me, my name is Samir Rahman, but non-Arab people keeps calling me Samir for no reason, I don't know. So you can call me Sam. I am the co-founder of Kali Technology Solution in Jordan, a company that specializes in linking artificial intelligence within the architectural solutions or the engineering solution over the blockchain. So we automate all the process of the BIM. Everyone knows what BIM is, right?
Yes.
Yeah, it's building information modeling. We automate all the process of building information modeling using artificial intelligence through the blockchain. Also, I'm the CTO of Severe Virtual Labs, and I'm an ML engineer from the MDFT Europe as a deep learning specialist. Also, I'm an architect, like you all guys from Philadelphia University. So we're gonna discuss what we're gonna learn in this workshop. This workshop is gonna be in English, with the little exceptions to repeat and re-explain in Arabic if anyone needs to be explained in Arabic. Okay, so we're gonna start with the introductory of machine learning and linear regression, supervised and unsupervised learning. We're gonna dive deeply into deep learning, which is the hidden neural network. And we're gonna learn how to project or visualize our neural network using the augmented reality. And last of all, we're gonna learn how to establish or generate a fractal design. Have you ever heard of a fractal design before? Like Mandelbulb, Uberbulb? Have you ever heard about it before? Okay. So I'm gonna be asking you guys, what is machine learning? Okay. We're gonna dive deep into machine learning. Before jumping into the code, we're gonna understand what is machine learning. We hear that term over and over. The recommendation list of the of your Netflix, the spamming filter. What is machine learning? What is AI? So, machine learning, in a nutshell, it's like a mimicry of a human thinking. Okay, I'm sorry, guys. Okay, it's a mimicry of a human thinking. So, when human thinks and realize something new, the neural system in the biological system understand what's happening in their environment. So when we try to adapt this technology or try to make our processor or our computer to think like us, we call it the machine learning. So the machine train and learns. So there's two types of programming, if you know. There's the low-level programming and the high-level programming. So in the low-level programming, we provide the inputs and writing the rules, the condition to get the outputs. When in machine learning, we provide the input and the output, and the machine learns from that sequences or that patterns and predict the rules of the input and the outputs. Guys, if you have any question about the terminology of machine learning or the traditional programming, please open your microphone and ask away, because I keep clicking the chat to read the messages. So you can freely open your mic and ask any question that you want. Yes, it's live streaming through the YouTube, okay? So we understand the difference between the low-level programming, the traditional programming, and the high-level programming, which we call it the machine learning. So the low-level programming, we talk about the providing the inputs and writing the rules to get the outputs. And when we talk about machine learning, it's a high-level programming when we provide the inputs and the outputs, and the machine learns the pattern from the outputs and the inputs to predict the rules. So it's like the reversal of traditional programming. So let's take, for example, we want to write a program that understand or realize if it's that a dog or a cat. If we're gonna do that in traditional programming, we're gonna need 1,000 and thousands of lines to write that program. When we use machine learning to provide all the possibilities of these cat positions or the shape and all the data set of the or all the images of a dog positions and shapes. So if we're gonna do it that in the traditional way, we need to understand that we need to provide in every position in order to write add an if statement to understand. So as we see here, we provide an image of a cat. If we put another image or a different image of a cat, it doesn't understand unless we write it specifically in the code. So if we provide another image of a dog or let's say not train, program the machine in traditional way in some sort of position of a dog, it doesn't understand the other position. But in machine learning, we provide the data set and it extracts all the features from these images to predict what's coming as a rules. So we provide all the images of the cats and provide all the images of a dog, and it does understand what's the input when the machine predicts the rules. So if we have these two lists of data set, let's say we have an X list and the Y list, and the X list is 0, 1, 2, 3, 4, 5, and the Y list is 1, 3, 5, 7, 9, and 11. Can you predict what's coming if we say a 6? Let's say we have another item of the X list as a 6. So what's the Y? Yes, thank you, it's gonna be 13. Now this is let's say the human learning or realizing the pattern between two lists. So your brain realized that the relationship between the list A, list X, and list Y is 2 times X plus 1. That's you're doing the machine learning in your brain, okay? So if we want to write the code of that machine learning using a Python, TensorFlow, PyTorch, whatever the tool you want to do, you want to define the model and the network, the neural networks with the number of neurals and the input of shape. We're not gonna jump into details in this coding material because the purpose of this workshop to do that on Grasshopper and to do that with the visual scripting. But I'm gonna explain what is happening here as a like high-level programming. So we define the model as a sequential from the Keras. Keras is the type of high-level API of TensorFlow. TensorFlow is a library of machine learning and deep learning. The layers is dense. Dense means you provide the number of neurals and the input shapes. Then we're gonna make the machine compile the optimizer that guesses the rules between two lists, two data sets, and the loss gives you the value if this guessing or this prediction is true or near that pattern between two lists. So we write the first list and the second list, and we put the fit of the model to try the loop, to try to find the to find the pattern between two lists. So epochs mean epochs or cycles mean we're gonna go through this relationship between two lists over and over 500 times to know the rules. Okay, then we're gonna print the prediction of 7, which would give us the 15. Okay, let's jump into Grasshopper and find the difference between the low-level programming and the high-level programming. Have you guys installed all the plugins that I've sent or in my GitHub repository?
Yes.
Okay. We're gonna go to Grasshopper and try to explain the low-level programming and the high-level programming. Okay, so can you see my screen clearly, right? Okay. So let's say we're gonna do the low-level programming. We have the first list as an input. It's 0, 1, 2, 3, 4, 5. Okay. We're gonna make it a multi-line data. Then we're gonna need a C# component to write a traditional programming using C#. Sorry. Okay. So in traditional programming, we're gonna provide the inputs and the rules to get the outputs. Okay. So the rules for us, A equal 2 times x plus 1, right? That was the rules of this of a previous example. So once we provide, sorry, A equal 1 plus, yes. And the type of this variable is double. So in traditional programming, we provide the inputs and write the rules for us to give us, as we know, the outputs. Okay? This is in C# programming. Let's say in high-level programming, we have this data set as a XS, and we need to provide, to have, sorry, the YS as a data set. So it's 1, 3, 5, 7, 9, and 11. So in the high-level programming, we provide the inputs and the outputs, and the machine trains over the inputs and the outputs and predicts the rule between, or the relation between the list A and list B. So when we go to Lunchbox and go to machine learning, this type of machine learning is called linear regression. So the inputs for us is this list, and the output is this list. So now when we provide any testing, let's say 12, if we provide that as an input to test our machine learning, supposedly it would give us the 25. So if we test that, we get a 25. Yes, you can talk freely.
Can you please use bifocal? It will be easy for us to follow you.
What is bifocal? I don't know.
Just to read, for example, the script, because now we cannot see, for example, the name of the.
Oh yeah.
It's a plugin. Yeah. So the name
like
of the component comes at the top.
Yeah.
Here, I don't know.
No, I think we have to install it.
From Food for Rhino.
Yeah.
Okay. Is it bifocal, right?
Exactly.
Yeah. What does it do? Again, I'm sorry.
It just creates, displays the name of the components. You just have to drop this bifocal on the canvas and you open any script. So it just displays the component's name at the top of each component.
Okay, so when I go to C#, yeah. Okay, do you know the trick of Alt Control?
Yeah.
This one, okay. When I press Alt Control, you can ask me that. It's okay. So I'm gonna repeat that. You're welcome. I'm gonna repeat that example again. Okay. So let's say we have the idea of this example to understand the difference between the low-level programming and the high-level programming, the traditional programming and machine learning. So when we have the list of, let's say, 0, 1, 2, 3, 4, 5, and we do as a multi-line data, okay, and we provide it here as a double or integer, whatever it is. So we provide the inputs and the rules in order to get the output. So the rules for us is 2 times x plus 1. Okay. So it gives us the outputs. Okay. So this is the low level or the traditional programming. If we're gonna talk about the high level programming, we're gonna have the inputs and the outputs, which is 1, 3, 5, 7, 9, and 11. And the machine learns from the inputs and the outputs to predict the rules between the lists. So we go to Lunchbox, machine learning, and we get the linear regression because the rules here are very with the linear algebra. Okay, so we give it the inputs and the outputs, and if we test that methodology with a new inputs, let's say 22, it will give us 45. So we see it here as 45. Let's try to change the second list and add 2, which means 2, 4, 6, 8, 10, 12. Which means 2 times x plus 2, right? Okay. We're going to provide the outputs and it does change automatically because this is machine learning. Is it understandable for you, the relation or the difference between low-level programming and the high-level programming? where do we put the random number? In the list or as a test? Okay, let's say we provide one of the outputs incorrect. Okay, let's say we do have here, this is 5. And provide it as is. We're not gonna get the result, or the prediction would not gonna be accurate, because one of the data set that learns has an incorrect value. That's why we need to pay attention to the data set when we feed it to the model or the machine learning to have an accurate data in order to get an accurate result or an accurate prediction. Okay? Okay. If you have any question, you can, like I said, open your mic and ask away. I don't have to bring the chat every time. Okay. Now let's get back to the presentation. Okay. By the way, all the materials is going to be uploaded to the GitHub account or the GitHub repository of the architectural intelligence. Okay. There are 4 types of machine learning. We have the unsupervised learning, we have the supervised learning, and we have the reinforcement learning. And there's the last one. We don't usually use it. We call it the semi-supervised learning. So what's the unsupervised learning? The unsupervised learning is providing the machine with unlabeled data. It's unnamed. It's not annotated data. Okay, so the machine only learns from the patterns. It doesn't understand what it means. Like if we say here, so we provide the machine with a couple of fruits images. It doesn't understand they are fruits. So it recognizes all the data and do the interpretation between these data and classify them. Okay, so it classifies this data as a item 1, item 2, item 3, and then we label these outputs. We call this unsupervised learning. The supervised learning, we're gonna learn about it in the next session. We provide a labeled data so the machine understands what it means and how to extract the feature from these data. But in unsupervised learning, it doesn't understand what these data are or the relation between these data. So it classifies them based on the weight of the neurals. Okay, we're gonna dive deeply in the weight of the neurals in the next session. So we have this input data, and the machine learns the pattern of these data and classifies them as is. So there are 2 types or 2 methods of unsupervised data. We call the first one is self-organizing maps or the Cohen network, and the other one we call it the adaptive renaissance theory. So what's the self-organizing map? Self-organizing map, we build a network on this data set and try to find or the correlation between this data set. So we build the grid between the data set and try to find the relationship between the data set in order to classify it. That's we call it the Cohen network or the self-organizing maps. We build a map over this data set. So it's fixed grid topology between these neurals, and we provide this data set or that grid. The nodes are neurals. So every neural gets to the data set, it wins over the other neurals. That we call it the self-organizing maps. We call it a competitive learning. So the neurals or the neurons compete within each other in order to get to the full data set. Okay? So the input presents the data vector in n dimensions. We're going to talk about the second dimension and the third dimension and the fourth dimension. And each neural is also reprinted in the n-dimensional space. I know you don't understand it completely, so I'm gonna break it down for you. Okay, so when we talk about that, this is the unlabeled data set. It's randomized. It's on that, let's say, on that chart. Okay, so the self-organizing map, it starts with defining this neural network as a topology or as a grid of 3 times 3. This grid, we call it the SOM grid or the self-organizing map. Okay, these nodes, we call it the neurons, sorry. So we have this grid in two-dimensional space, and each neural try to find the neighborhood of the data set. So it starts comparing the data samples to neurons in random order. Find the closest fit instead of neurons, the winner neuron. So this neuron finds the data set and moves slowly to that neurons. So we adjust the winner neurons position to respective data sample according to predefined learning rate. So every neurons will spread out the new position or the updated position over and over to other neurons in order to that grid to move slowly to cover all the data set. So it spread out the position update information to the winner neurons to political neighbors and adjust the neighbor neurons position according to predefined neighborhood function. And that repeat based on the epochs. We heard about the epochs or the cycle of training, a training cycle. Okay, it starts moving in order to cover all the input data. We're gonna see that clearly in the next example. So as you see, you provide the data set of the randomized data set over that chart, and the SOM grid starts to spread over this data set in order to understand or to classify this data in the second dimension. We're gonna see that now in Grasshopper. Okay. Okay. First of all, let's say we have like random data or random points, a populate points. So we provide, first of all, we provide the boundaries of the shape. So we're gonna go rectangle, and we're gonna provide this space in order to separate random points as a data set for us. So in order to make a populate in this boundaries, we use populate 2D. Oh, sorry, bifocal. Okay. We're gonna use populate 2D in order to populate over this region. And we're gonna provide the number of, let's say, the count of these points. We're gonna say, let's say 27 points. Okay. I believe everyone knows Grasshopper, right? Does any one of you don't know Grasshopper? Okay, good. Okay, so the seed, it generates random position or shuffle these over this region. So we have this population and we're gonna move them. We have this random points. We're gonna move them on the Z axis randomly. So we're gonna use move, and we're gonna move these points on the Z axis, and we're gonna use random component in order to move this point randomly. So the number we're gonna provide it by the list length from the population, and we're gonna give it a starting domain and the end domain, which could provide a random number between these regions. Let's say 100. The z-axis and to the okay, we're gonna spread that. Okay, that's our data set. It's randomized from the populate 2D, and it moves in the z-axis in random position. Okay, in order to start the self-organizing maps, we're gonna go to Crow, and we're gonna provide a CrowNet constructor as a 2D map. Okay, so what is the layer width and the layer height? So it's the number of the grid, number of the neurons on the grid. As you see here, the number is 3 times 3, so we're gonna provide the number of neurons. The more you provide neurons, the more accurate you can get. Okay, so let's say 40. Okay, is it circular rows or circular columns? No, it's not. It's rectangular grid. So the lattice topology, it's rectangular, and we can experiment on the hexagonal lattice. Okay, the neighborhood function, we're gonna discuss that on the next session. Yes, Bushra?
I want to ask if the nodes should be the same quantity of the spots or the points of the data set?
No, they don't have to be at the same number of the data set. The data set is randomized with the number of the list and the number of the items, but the accuracy of your network or the neural network, it depends on how do you define the layers of your constructor or the CrowNet constructor. Okay, so we don't have a circular rows or circular columns. The grid, we have rectangular, not hexagonal. And the learning rate, it's the accuracy of your network. So the higher number with the maximum of 1 and the minimum of 0, so the higher you can get, the more accurate your model would be, based also on other principles. So let's say it's the learning rate is 95. Now we have the CrowNet here, but it's unprocessed because we need to process it through the SOM engine in order to train it. So we have this data set for us. Now let's move and create this grid using let's say a mesh plane, because I need the neurals to act as a points in order to visualize it in Rhino. So we're gonna start to find the average plane between these points, and to find the average plane between these points, we're gonna get the plane fit, I guess. So plane fits, it's generate an average plane between all these points. So when we provide it, we can see it as an average between all these points. Okay. And with that provided, we're gonna make a mesh plane here with the same division of the width and the height of the network. Okay, so we're gonna start with rectangle. Okay, and the plane is that one. Let's say no, the X size and the Y size. Okay. Now we're gonna generate the generate the mesh plane using a mesh plane. And what's the number of the width count and the height count? We're gonna provide the height count and the width count as same as the width and the height of the noodles. Okay, so we have 40. We're gonna provide 40. In order to visualize these noodles as points, we have to provide the mesh plane with the same number of the neurons. Sorry. Okay, we have this mesh. In order to get the point, we use deconstruct mesh to get the vertices. Okay, and in order to get them ready to be trained, I need to split them with the same, let's say the same number of the height and the width count. So I'm gonna split these numbers because all the vertices here are flattened in one list, but I need to split them into, we call it a vector, a learning vector. So we're gonna split them into number of branches. Okay, so we use the partition list, I guess, and they need to have the same number of items in each branch. So we're gonna provide this one in additional to 1, I guess. Yes. So we have here a 40 and 40. That means 1600, but we can see here it's 1681 vertices, which means the mesh plane takes a +1 of the input as a width count or the height count. So we're gonna provide the size with the +1 to make an expression of x +1. We can see all here as simplified data. They have the same number of items. Okay. Then we're gonna bring the CrowEngine self-organizing map. This is the training cycle, or the epochs, as we discussed about it earlier. So let's say the training cycle is 6,000 because it's a big network. Sorry. The CrowNet is our network that we constructed earlier. Okay, and the training vector is the chunks. This is the training vectors. So we present the neurons as points in order to visualize them. And the data set or the points are this one. We're gonna shuffle them randomly. These points are generated randomly, but we're gonna shuffle them in order to make it more complex. So we're gonna shuffle the order of this list by using jitter. So what does jitter do? It randomizes the order of the data set or the branch of the list of data. So we have this list of data. We're gonna provide it here. As the points. And in order to start training, we flip this into a true value. But the output is gonna be a crow model. So we're gonna visualize what's coming from this engine using, I guess, the 2D sum point display. So it takes the CrowNet. Okay, I'm gonna re-explaining what jitter does. Okay, so let's say we have this data set or list of data, sorry, these points. Okay, so if we take the first item from this data, sorry, if we take the first item, it's that point. Okay, and if we use jitter, we see it's a different point. So what does it do? It randomizes the order of these elements inside that list. So if we wanna randomize the order of a list of data, we use jitter. It randomizes the order of this list of data. So we use another seed. Is this the first one? And we keep randomizing or shuffling the data. Okay. So before start learning, we're gonna display the points, these points, the movement through the learning, or visualize the neurals through the training cycle. Okay. Also, I'm gonna let me hide these. Okay. Also, I'm gonna visualize or display the grid of the 2D self-organizing map. So it needs only the CrowNet to visualize it. Now, once we go to the top and start training, let's go like that and zoom in. This version of Crow, it's a little bit buggy, so let me see what is happening in the training cycle. Yep, like I said, it's a little buggy. We can say See, it's kind of buggy here, but we're gonna make it 6,000. Yes. You see, the machine tries to find the best way to cover all the data set we have in here through the Kohonen network. So as you see, it's trying to cover all this data in order to make the full network between these data. So when you see in perspective, it didn't cover all the data that we provided, which means we're gonna need to provide more neurons in order to cover all this data set. So we're gonna turn it off, and let's say we have 60, and we will try again. Yes. It's okay, man. I give it like 6,000. I'm really sorry, it might take some time. But the more you give it, more cycles you give it, the more accurate it will be. So we're gonna see how it's gonna act.
Sam, I have a question. So you put the learning rate as 0.95 and you said the higher it is, the better it is.
Yeah.
So why didn't you say 1 and why did you keep it at 0.95?
95? Yeah, you're talking about the learning rate?
Yeah.
Once there's two things in machine learning. There's something we call it the overfitting and the underfitting. So when we provide the network with the, let's say, a 100% of learning rate, it sometimes generates a model that's overfitting, which means if we provided a simple or a simplified data set, it fails to achieve it. And the underfitting, when we provide the learning rate with the lowest value possible. So when we provide the inputs or the data set with more complexity, it fails to train it. That's why we don't take the 100% or the 1, we take a little lower, okay? So 25, 95 or 98, 97, but don't like put, 100%.
Yeah.
Okay?
Thank you.
Welcome. As you see, it provides, now you understand the Kohonen network. So it provides the network between all these data sets, the data set or the input data to give us the network between these data. All right? So we can see it as a winner points, the winner points who got into the actual data. So we call the winner neurons, and we have the grid of this data. Now, can we convert that grid into a mesh? Yes, we can using the Crow 2D SOM mesh display. Oh, sorry. So we just connect the CrowNet and we see it as a mesh to us. Okay, but I forgot here I provided a hexagonal topology. So we're gonna turn it off and keep it that way, but we're gonna provide the rectangular, which is the 0. As we see here, the type of the grid of the lattice, it's a rectangular or hexagonal. It depends how do you construct your noodles, okay? It's a type of grid. So we're gonna provide the rectangular lattice or the rectangular grid. So now we're not gonna see a triangulated grid. We're gonna see a quad grid, but we're gonna bring it down to, let's say, 3000, and we're gonna turn off the Crow mesh, and we're gonna try again with unfortunately this engine or this machine learning, we're using the CPU, but if you follow me on Instagram, you see I'm bringing the torch into Grasshopper in order to use the Coda or the GPU, which would give us like 10 times faster than the CPU, like, you know. So which give us the third perspective, and we can easily use the CrowNet mesh to give it a mesh. By practicing, you would understand more and more about the Cohen network and how it does work, and how we can embed that example into architecture. Was that example clear to you what SOM is, or what self-organizing map? That the self-organizing map through the data set. That's type of unsupervised learning. Do you guys have any question? Okay. Do you want me to upload all the assets that we're using into GitHub? Like all the codes that I'm testing or I'm showing right now?
Yeah, if you can.
Yeah, no problem. Okay, let's move with the Cohen network or the SOM into a 3D and see how it does. Okay. So if you bake it, yes, we can see here which data set is the winning points, and we can use the similar component to find which path from this data set, okay, or from the grid. These are the winning points who got into the data set. So As you know, we can use a similar component, I guess, to find it. Sorry. Find similar member, yes. So you have the data and the set, and you can find where the points are, or the winning points, the winning noodles. Okay. You're very welcome. Okay, let's move on to the n-dimensional or the third dimension. I know this considered this example considered as three-dimensional, but we're experimenting here on points, so we're gonna test that theory or test that method on 3D objects. So let's get started with the new. Let's make the most randomized data set that we have. So I'm going to be using a lot of random to generate random numbers of a random data set of random shapes. So let's first of all generate random points. Okay. Let's pick up a range between minus 5,000 and minus 500, sorry, and 500. Range, okay. Also the numbers of that, let's say 10 points. 10 points will generate 10 random shapes with the 10 random vertices. So we have this range, and we need to modify or change the seed, because technically they're gonna have the same number. So we're gonna make random, okay, and the number is 10, number is 3. And we could provide the same range or make a new one by constructing a domain and make a new one for the randomization. So let's say from 20 to 2000, and that's the new range, and we're gonna get only the integer number, so that it's gonna give us a seed. So list of item, and every component takes a new seed. In that case, that would give us 3 different lists. So we have list number 1, list number 2, and list number 3. Without the different seed numbers, we're gonna get the same list. Okay, so we're gonna get seed 1, seed 2, and seed 3, and that will construct a vertex for us, or vertices, sorry, points, whatever. Okay, these points, we can control the distance between these points by changing the domain, and the shape of these points, or the position of these points, we can change it by changing the random. Okay. Now we're gonna construct a plane from these points. So we have this, and we need a random x-axis at least. So we're gonna need these, or let me just construct them. Okay. So this is for the new one. And I'm gonna say it's 6 numbers. So now we have a new 3 lists that has a unique seed number in order to generate a vector and that vector would be an x-axis. So as you see, every point has a different and unique plane, and we can control it by defining seeds. Okay. Okay. From these planes, we're gonna construct a center box using primitive surface, I guess, surface, primitive, and center box. We could add a random number to the x and y and z, but I'm gonna keep it fixed and say, let's say, okay. Okay, from these boxes, we're gonna construct random points or generate random points using Populate 3D. So Populate 3D, we're gonna take these regions and we're gonna give it a random number of points by using another random. I'm trying my best to randomize all the data set as much as possible in order to find how some will find the correlation between these data set. So let's get a new one, and we find 7, and that will give us a random number. We're gonna take the integer and it has some negative number, so we're gonna use absolute. Although the numbers here are very high, so we're gonna need a new constructor or domain constructor because the numbers here are very high for count of number, for count of vertices. So let's say from 8 to let's say from 8 points to 18 and give it to a new range. We're not gonna need the absolute. That would give us random number of or random count. So each one has a random number of points. And from this population, we're gonna construct a mesh using 3D convex hull, or you can use Delaunay cell 3D. So we're gonna use a 3D convex hull to generate a random shape, and each shape has different identity from the other one. See, it's a different identity. And we can make it, let's say 5. So some shapes have a higher number and some shapes have like low number of vertices. Okay. Also, we're gonna construct a color for these meshes using a mesh color, and we're gonna use a color, let's say HSL, hue, saturation, and luminance. And we're gonna provide like a random number for hue to generate random colors using also random components. So the hue takes from 0 to 1 as a range, so we don't need the this one, I guess, I believe, or disconnected. The number 10, yes, and we don't need integer, we need like float number. So that will give us 10 different colors, and as we see here, it's the branches, or the tree structure is graphed. So we're gonna graph the colors in order to give every element a unique color. So we're gonna graph. We're gonna graph these colors and give it different. Each shape has a different color from the other. So now we're gonna construct the Cohen network, or the SOM grid, but this time we're gonna need the 3-dimensional grid. So we go to Crow, and we see here Crow constructor is generic, or the n-dimensional Cohen network. Okay, so we need a layer dimension. Like we see, in order to construct the Cohen grid in 2D, we provide the width and the height. So since we have now a 3-dimensional grid, we're gonna provide 3 numbers. And let's say that 3 numbers are, we're gonna need a pool, Genie pool, in order to provide more, like multiple sliders. So we're gonna need a 3, since it's a 3D grid, 3-dimensional grid, and we're gonna use an integer number, and let's say 10, 10, 10. We could, let's say 15. Okay. It doesn't have to be the same number. All the layers doesn't need to have the same number, so you can provide it, but the more